So for 3 Riemann sums and definite integrals, today we are going to just do the Riemann sum part of it, and then tomorrow we're gonna show you a method to solve definite integrals that is a little quicker than what I show you today. And there's a reason I don't show you both in one day, because you'll skip the one and just go straight to the other one.
Darn.
I know.
So you're showing us the one that we can skip first?
No. Okay, so what we're going to do, you don't really need to particularly write this down because we will go step by step by step in a minute. We have the equation y equals the square root of x. So that's what this would look like if it kept going, right? And I'm going from 0 to 1. So what you do with that, should have gone clear up into there. We're going to use a limit method. So we have the limit as n approaches infinity from I equals 1 to n. And you notice that n are these increments, and they are not even, are they?
No.
No, they are not nice even steps. So we've talked about over and under estimates. So we want to take your over and your under and combine them so we get a better approximation of the area under the curve. So we will stick it into the limit formula that I show you in a minute, and we have the width, we have the length and the width here, and we're going to, we know that 1 over n cubed, well, because I have n squared, and n squared would be n to the, no, I don't, sorry. We have the square root of n squared, which is n, square root of n squared, which is n, yes? Mm-hmm. Times n cubed, n squared is n cubed. So we can bring that out.
Yep.
And so then I have 2i squared minus 1, or minus I, not 1. We have a definition for I squared, don't we?
Yeah.
Yes. Which is 2 times n plus 1 times 2n plus 1 over 6. And the 2 is out in front of it. And then we have a formula for I, which is n times n plus 1 over 2. So you will need to write them again on your homework or know where they are in your notes so you can use all those. And we combine all this stuff and get this. So when we do the limit, well, this would be 4n cubed divided by 6n cubed, which that would be 4/6, correct?
Yeah.
And 3n squared divided by 6n cubed would be 1 over 2n, reducing. And negative n over 6n cubed would be negative 1 over 6n squared. And as my limit approaches infinity, these would zero out. And 4/6 would be 2/3. So the area under here is 2/3. So if I made a rectangle here, this area would be what? 1/3.
1/3.
Since this is 2/3.
Yeah, but you said if I draw a rectangle,
I didn't realize
you
that
didn't
was
scribble it in yet.
Yeah. So if you drew a rectangle, the bottom is 2/3, so the top would be
1/3.
1/3. So you would be able to find both the area under the curve and above the curve by doing this. So what we did was Riemann sums, and I will go through the definition right now. Okay, so we have let f be defined on the closed interval a to b, and let delta be the partitions of a to b given by a equals x sub 0 is less than x sub 1, which is less than x sub 2, and so on all the way down to b. It's cutting the interval a, and b into portions. That's all that's doing. Okay? Where change of x sub I is the width of the subinterval and of the ith subintervals, if C sub I is any point in the ith subinterval, then x sub I minus 1, comma, x sub I, then the sum is. And this is where you need. You don't really need all the other stuff. You need this right here.
We don't even need
Is the Riemann sum. Well, this just tells you that C sub I is somewhere between the lower limit and the upper limit. That's all that's saying. Okay, so we have the sum from I equals 1 to n of f of C sub I times delta x sub I. This is called the Riemann sums of f of partitions delta. So there's some things we also need to know. We need to know what C sub I is. We also need to know what delta x sub I is. And it should come up as soon as I hit this next thing. There it did. Okay. Oh, there's missing an I on right there. So delta x sub I is b minus a over n, and C sub I is a plus I times delta x sub I. Oh, and that did change. If you notice from the top, it says the definition of a definite integral.
Yes.
And so it takes your Riemann sums and uses it to find a definite integral. So the difference between an integral and a definite integral, before you've had them and they just were the integral sign, correct?
Okay.
Now we are giving them limits, so that's why it's called a definite integral.
We're supposed to write that, the one in the box down too.
You can just put this part in front of what you wrote, because this is the same thing as what you just wrote. So finding the Riemann sum is the same as finding a definite integral. Now, this is equivalent to the long way of finding a derivative. Because the long way to find a derivative used a limit, correct?
Mm-hmm.
So this would be considered the long way to find a definite integral. Let me know when you guys are ready.
Yep.
Oh, and I didn't point out that A is a lower limit, B is an upper limit. I would assume you would know what I was saying when I would say upper and lower limit. Okay, so this is something, just a little side note. It's theorem 4.4. It's continuity implies somebody want to say that for me? Because
Integrability?
you can find the integral if it's continuous. That's what it's saying. Okay? So if a function is continuous from A to B, then you can find the integral from A to B. It doesn't say the whole thing. It says if it is continuous in this portion. Can anybody think of an example of a function that would not be continuous over all real numbers? Remember, continuity was holes, gaps, or sharp points.
Whatever a step function is, a time-wise function,
Oh, piecewise function.
piecewise function,
Piecewise function would not be, what's this one?
absolute value.
An absolute value would not be at here, right?
Yeah,
But could I find it like here?
from there to like,
Yeah. So as long as it is continuous from A to B, then you can find the integral of it. If it is not continuous, you cannot, just like if it was differentiable, it had to be continuous at that point, correct?
Yeah.
Yeah, I can't even say that. Integratable. There we go. I can't look at the word while I say it.
Integratable.
It's integratable would be this word right here. Yes?
No,
There's
because
no
there's no
T.
T.
You're putting a T in.
You're adding a TE in there.
Integratable.
Integrable.
Ah. Okay. Evaluate the definite integral by the limit definition. So this is every problem you have today. This is your instruction.
With the
With what I just,
S thingy.
yes, but it's the limit.
That's
So we're going to have, oops, go back. So we're going to have the limit
What? Oh,
as n approaches 0, because we changed the delta x to just n.
did we?
I think it did the second time, but it's okay. From the sum from I equals 1 to n
Kill.
of f of c sub I times delta x sub I. So the things we first need to figure out are c sub I and delta x sub I. And you're,
Alright, give me a second.
this picture is just so you can see. So this is from -2 to 1 of 2x. So that has a y-intercept of 0 and a slope of 1, correct? So if I did y-intercept of 0 and I counted up 2 and over 1 and down 2 and over 1 and down 2 and over 1. So it would give me this line right here. But we're only going from -2 to 1. I don't want anything else. So we need to figure out delta x sub I.
So that's gonna be,
So it's b minus a.
yeah,
So b is 1 minus a -2 over n.
uh-huh,
So that gives me 3 over n.
yeah.
Okay? And c sub I,
What? Oh, that's why there's not a negative part, yeah.
I thought there was.
No, it's just the.
okay, and c sub I is a. Well, what's a?
-2.
Is -2 plus I times delta x sub I, so it would just be 3I over n.
Yeah,
So you cannot do any of this until you've found delta x sub I and c sub I. Now my formula just says limit as n approaches 0 of the sum from I equals 1 to n. And it says f of c sub I. So that means we have to put c sub I into the function. The function is 2x. So it's going to be 2 times -2 plus 3 over n.
What is 3I over?
Oh, I forgot my I. 3I over n. And then times delta x sub I. Well, what's delta x sub I?
3 over n.
3 over n. So knowing our summation rules, I have a 2, which is a constant, and I have 3 over n, which is also a constant, correct? So I can multiply those together and bring them outside of the summation. So we have the limit as n approaches 0 of 6 over n times the sum. Now we're only left with this, correct? The negative 2 plus 3i over n. So when we have the addition, we separate them into 2 different integrals.
Yeah.
So I'm going to write it out and then we'll separate it. So I have of 2 plus 3i over n. So we now have the limit of n approaches 0 of 6 over n of negative 2, the sum. And I quit writing the limits, but please know they're still there. It's really hard to write this small so it all fits. And that would be 1 if I factor out the 2. And on this, we would have plus 3 over n times the sum of I. See how I'm pulling out those constants. I'll put my 1 to n so we can see it. So I have the limit as n approaches 0 of 6 over n times, well, when it's just 1, it would be the constant times the upper limit, correct? So it would just be negative 2n plus 3 over n times, what's the summation rule for just I?
I don't really remember.
N times n plus 1 over 2. I would encourage you to rewrite those on your paper or in these notes. Okay? So I'm now just going to do some simplifying. Well, this n here and this n here can reduce, can't it? So if I distribute, so the limit as n approaches 0 of, well, negative 2n times 6 over n, I think that's negative 12, yes? And then this 2 would reduce the 6 to a 3. Yes?
Yeah.
So I'd have 3 times 3, which is 9. And I'm just kind of doing this right here as n over 2 plus 1 over 2, correct? So I have 9 over n times n over 2. Pretty sure the n's cross out and I have plus 9 halves.
I mean, if you're pretty sure that's good enough for me.
Well, the 6 and the 2, wait a second, nope.
Alright, then it's not good enough for me.
Because the 2 reduced the 6 to a 3, right?
Yeah.
So the 2's gone. Sorry, so we have just this. So we have 9 times n.
9n plus 9. So then we have negative.
Oh, we had 9 over n. See, I'm trying to skip too many steps. Let me write it in red. So this right here is 9 over n. And we're multiplying it into here. Yes? Okay, so the n's reduced and I'm left with 9. And then I have 9n times 1, which is, or 9 over n. 9 over n. So now are we ready to evaluate the limit? Have we simplified everything? Yeah. So if So if n approaches 0, so this, the 9n is going to become what? 0. And negative 9 plus, negative 12 plus 9 is? Negative 3. That should not be 0. This should approach what? Don't you think it probably should be infinity? If it's going to become 0?
Doesn't matter.
Well, it does, because you can't divide by 0. Okay, those all become infinity, sorry guys, because the number of n's are the number of divisions. So if we want this to get better and better and better, it's going to be infinite number of partitions. Sorry. Couldn't read my own writing. I'm like, there's something wrong with that. So we're going to do that. We have 2 more times. I'm going to do it with you, and then you're going to be on your own. Ready?
2 more times.
Okay. So the integral from 2 to 6 of 8 dx. So what is the first things we need to find?
Delta x sub I and c sub I.
So we need delta x sub I, which is b minus a. So 6 minus 2 over n, which gives me 4 over n. So these are the length and width of these rectangles is what we're finding, guys. And c sub I is
Where is the equation?
what?
Where's the?
It's
No,
3.
that's the problem.
That's
No,
the
that's,
problem number. Or the part of the
I don't even know because it's not problem 3.
Yeah, it's
Well, that's
problem
what I
2.
didn't think.
Okay. It's nothing. Okay, so c sub I,
Is
a, what's a?
2.
2 plus I times delta x sub I, so it would be 4I over n. I think that first one was obnoxious because this one is not that bad. Okay, so the integral equals the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I. So that means I have to plug c sub I in for the x. Is there an x there?
No.
No. So it's just what? 8
Yeah.
times change of x sub I, which is 4 over n. Well, 1 over n is a constant, right?
Yeah.
Yes. You can do it different ways. I pulled out 6 last time, and I probably would have left it in. Not 6, the 2 or something. I don't know.
6.
Okay, so I have 1 over n, the sum of 32. So I equals 1 to n. Well, 32 is a constant, correct?
Yeah.
So we have the limit of n as n approaches infinity of 1 over n times would be the constant times the upper limit, so 32 times n, which gives you what? 32. So the limit as n approaches infinity of 32 is what? 32. It's nice when there's no x, huh?
Yeah.
Ready for the next one? there's an x. Okay, yeah, don't even pay attention to that. Okay, so the integral from -2 to 3 of x dx. So the first thing we need to find is delta x sub I. So b minus a. So 3 minus a -2 over n. So we get 5 over n, excuse me. And c sub I is a, which is -2, plus I times change of x sub I, so 5I over n. So now I have the limit as n approaches infinity of the sum from I equals 1 to n. And I'm going to tell you I is called a dummy variable because could I change that to an x? Could I change it to an r? Could I change it to anything I want? Yeah, so they're called dummy variables. Okay, now I need to do my Riemann sum. So it's f of c sub I. So I just have x, so I need to plug in c sub I. So -2 plus 5I over n times change of x sub I. So it is 5 over n. How do you guys want to simplify it?
By watching you do
Do you want to multiply them together?
it. Yeah.
You want to pull out a 1 over n and then distribute a 5?
No.
Hmm?
No.
No? So you want to distribute the 5 over n?
Yeah.
Okay.
No, that's what I would do when I look at it.
Okay.
So I don't know really what else to do.
So that gives me -10 over n. Can I at least separate this?
No.
Of 25I over n squared? Yes? So now what do you want to do?
Why'd you have to rewrite the end thing?
Because I separated it. I separated at the addition. After you do summations long enough, you just do them. You don't actually rewrite them, but I was being nice to you.
Next we need to
Well, the first one would be -10 over n is a constant, yes? So it would be -10 times n over n. Because you take the constant times the upper limit. And -10 over n is the whole thing's a constant, yes? So we have that. And over here, we do need to, I would pull out the 25 over n squared. And this I right here, What's the rule for that summation?
N quantity n plus 1 over 2.
Okay. Getting rid of the summations just makes me feel better. I try to do that as soon as possible. Okay, so now we got to do some work. These two n's reduce, yes?
Yeah.
Okay, so I have the limit as n approaches infinity of negative 10. Well, I have this 25n squared times, well, wouldn't one of the n's reduce out?
Yeah. 25.
So remember that n plus 1 over 2 is n over 2 plus 1/2, correct? Okay, so then I'm going to multiply 25 over n times n over 2, which would give me what?
25 over 2.
25 over 2. And then I'm going to take 25 over n times 1 over 2, which would give me 25 over 2n.
Yeah.
So probably need to evaluate the limit. Well, the only thing that would change is the 25 over 2n would become what?
0.
0. So that I would have negative 20 over 2 plus 25 over 2. So my answer would be 5 over 2. So will you have times you can reduce it more quickly than others? Yes. I think the summation was that in 4-1, or I think it was in 4-1, wasn't it? Or was it in 4-2?
It's 4 2.
It was 4-2?
And it's on the page before this one.
Okay.
Thing.
So make sure you have those available to you. You might have some squares going on in there. But you only have, what, 6 problems?
Ew.
Questions, guys? Can you rush yourself through these?
Probably not.
Probably not. Please do them tonight so you understand what's going on tomorrow when we do the short version.
Well, I'm busy tonight.